So we'll end this video with an example. So let's consider aerodynamic drag on a rectangular plate. Consider that we want to experimentally characterize the drag force, the so-called form drag, FD, on a rectangular plate produced by the flow of fluid perpendicular to the surface. An application for this would be determining the wind load on billboard signs. Of course, the wind load on those signs is important for designing the support structure. So you're told that the drag force is a function of the fluid velocity, the fluid properties, rho and mu, and the dimensions of the rectangular plate. The plate has height h here and width w. And given these variables, we want to determine the dimensionless parameters, the pi terms, needed to conduct an experiment to characterize the drag force. And I'll remind you that this is a variation on the example that I discussed in the video for part 1. So the first step in the problem is to list the n variables. In this case, you're told in the problem statement that the drag force is a function of the size of the plate, so width and height, velocity, dynamic viscosity, and density. So we have 6 variables. Now, it's a common mistake to actually just count the variables, the independent variables here, and come up with 5. So don't forget to include the dependent variable, the thing you're after, in the count. So there's actually 1, 2, 3, 4, 5, 6 variables. Now, if you think about this for a moment, this problem about characterizing drag on a plate, surely the area of the plate matters. The bigger the area, the more drag there is on the plate. So why didn't we include the area of the plate as one of these variables? You might pause the video and think about this for just a minute, and then I'll give the answer. The answer is because the area of the plate is equal to the width times the height. So area is not independent. We've already included h and w in our list, so we don't want to include area because it wouldn't be an independent variable. If we included area, we'd have to take out one of h or w. We could include area and w or area and h, but we can't include all 3. So we've done a check that all the parameters are independent. So step 2 is now to express all the variables in terms of their basic dimensions. And I'm going to use the mass, length, time, and temperature scheme. You can use the force, length, time, and temperature scheme if you like. So here I've listed each of the 6 variables. So the drag force, of course, in newtons would be kilogram meter per second squared, so that's right. Width has dimensions of length. Height has dimensions of length. Density is mass per volume, so mass over length cubed. I'll come back to the units for dynamic viscosity in a moment. Velocity is length over time, so that's correct. Now, you can go to the table and look up the units for dynamic viscosity, but suppose you're on an exam and you're not given that table. Well, there's no need to memorize the dimensions for dynamic viscosity. You can deduce it by knowing Newton's law of viscosity. So if you know tau equals mu du dy, now that you should memorize. That's a basic piece of knowledge that you should have at your fingertips, just like F equals ma and V equals IR. It's a very basic equation. So once you have that basic knowledge, you can deduce mu from the fact that it's tau over the velocity gradient. So tau is a stress, so stress is newtons per square meter. And then we have a velocity, meter per second. Of course, it's on the bottom, so it's meter instead second on the top. And then dy here is a distance, and it's on the bottom of du dy on the denominator, so it comes up on the top. So we can cross this out with this. Now I've made that substitution, and I've still got second over meter squared here, and we can cancel that with that, and we can cancel that with that, and you can see you get kilogram over second meter. So you can deduce in just really a few seconds that the dimensions of dynamic viscosity are mass over time times length. So there's no need to memorize this, but you should know Newton's law of viscosity. So now we've figured out the basic dimensions in all our variables. Now it's just a matter of counting. There's 3 basic dimensions. There's j equals 3 basic dimensions in our variables. We have mass, length, and time, and that'll probably be the same in all of the problems you do, unless you're dealing with a problem that's not isothermal and you have some temperature involved, some heat transfer. And we have 6 variables. We counted them in the previous slide. So the Buckingham Pi Theorem says that we have k equals n minus j, so 6 minus 3. So we have 3 dimensionless numbers or dimensionless pi terms that are going to describe the drag force on this plate. So now we go after getting those dimensionless pi terms. We do this step 4 by selecting j equals 3 repeating variables from our list of 6 variables. And I've listed over here, I've shown over here, there's our generic problem. There's our 6 variables. And we need to pick 3 of these as repeating variables. And there's some rules for repeating those variables, that I've listed here again. So we don't want to pick independent parameter as a repeater. So we certainly don't want to pick FD. And whatever 3 we pick, all of the dimensions, mass, length, and time have to be in those repeaters. And the repeating variables themselves cannot form a dimensionless product, and that requires a separate check. So I have somewhat arbitrarily selected 3 repeaters. I've selected W, V, and rho. Other choices are possible and completely correct as long as they satisfy the 3 rules above. So let's check that the 3 conditions above are satisfied. Of course, we haven't picked FD, so we're okay on that. Let's check that all the reference dimensions are included. So I've written down the dimensions here. W has dimensions of L, velocity, length over time. Density has mass over length cubed. So we have all 3. We have mass, length, and time included in the 3 that we picked, so it satisfies that requirement. The last requirement is that the repeating variables themselves can't form a dimensionless product. I like to do this very rigorously to make sure this can't happen. So what I do is I write down the 3 repeating variables, W, V, and rho, and I write them with exponents, A, B, C. So W to the A, V to the B, rho to the C, and now I've written the dimensions in here. So I've substituted the dimensions in here. So that's what I've got here. And then I've expressed them as exponents A, B, C. And the question is, can they form a product where the exponents on length, mass, and time are all 0? Is that possible? Well, to check that, what you do is you match exponents on the left and the right. And so now what I'm going to do is I'm going to start with mass. Now, mass here is raised to the exponent c, and it doesn't appear in any of the other terms. So in order for this to be dimensionless in terms of mass, c would have to equal 0. So that term goes away. Next, I look at time. Time only appears in this term. In order for this product to be dimensionless, b would have to equal 0. And now we're left with only this term here, and the only way it could be dimensionless, because it contains the dimension L, is that a equals 0. So that tells me that therefore non-zero values of a, b, and c do not exist that would produce a dimensionless term. So there's no way that these 3 variables can form a dimensionless term, and we've satisfied that third requirement up here. So step 5 now, we form our 3 pi terms. Remember, we have 6 variables and 3 basic dimensions, so 6 minus 3 means we have 3 pi terms. Okay, so we've picked W, and we've picked V, and we've picked rho as our repeating variables. So one by one with f, h, and mu, we go and we form these dimensionless products. And I've written down all three here. So in the first dimensionless product, we pick fd. The second dimensionless product, we pick h. The third dimensionless product, we pick mu. And these are the repeating variables raised to these unknown powers, a1, b1, c1. So for the first term, the first pi term, we use the drag force. For the second pi term, we use the non-repeater h. And for the third pi term, we use the non-repeater mu, the dynamic viscosity. And in each one of those pi terms, we've got these repeating variables raised to unknown exponents. Now what we do is we go one by one and we determine what those exponents must be. So we start with pi 1 and we determine what a1, b1, and c1 must be in order for it to be dimensionless. And that'll give us pi 1. And you'll see in the next slide that this is surprisingly easy. And then we go to pi 2 and pi 3 and do the same thing. And that gives us our 3 pi products. So let's go one by one, starting with pi 1. So starting with pi 1 now, I'm using the term that has as the non-repeater the drag force. We have our repeaters. I dropped the numeral 1 on A, B, C just to make things simpler. So we have W to the A, V to the B, and then density to the C. Now what I've done over here, I've substituted in the dimensions. So force has mass, length over time squared. W as unit has dimensions of distance, velocity, distance over time, and mass over length cubed is density, so that's correct. Now what we want to do is we want to figure out what A, B, and C have to be so that there's no dimensions, so that this pi product is dimensionless. So we have L to the 0, M to the 0, and T to the 0. And the way we do this again is we match exponents on the left and right side. So I'm going to start with the exponents for M here. So let's look at the exponents for M. Well, here we have M to the 1, so that's 1. And this doesn't have M, this doesn't have M. Here we have M to the C, so C, and then on the right-hand side, M has to have the exponent of 0. So in order for this to be dimensionless, 1 plus C has to equal 0. That tells us that this exponent here, C, has to equal minus 1. Now we repeat the same procedure, but now for time. So we look at the exponents of these terms. T squared appears on the bottom here, so that's minus 2. There's no T here. This is going to be minus 1. And there's no time in the density term, so we don't include that, and it's got to all add up to 0. So on the right-hand side. So that gives then that B equals minus 2. And now we do the same thing for the dimension of length. Here we have a L to the 1, so 1 plus A plus B minus 3C here, because L cubed is on the bottom and we have a C here, has to equal 0. So 1 plus A plus B minus 3C equals 0, and that's obtained by looking at the exponents on the left and right side of this expression. And now I know what C and B are, so I've solved for A, and that gives A equals minus 2. You can check my arithmetic there. So now we have A, B, and C. I'm just going to substitute them back in here. So this is minus 2, B is minus 2 as well, and C is minus 1. The first pi parameter is FD, W to the minus 2, V to the minus 2, rho to the minus 1, and then I've just rewritten here, rewritten that expression. So we get FD upon W squared, V squared rho. Now remember, we want to check that this is dimensionless to make sure we've done our analysis right. Remember from Bernoulli's equation that rho V squared is a pressure, it's a dynamic pressure. So this we know from Bernoulli's equation. We could check it in other ways if you wanted to, but I know from working with Bernoulli's equation that rho v squared is a pressure and W squared is an area. So pressure times area gives a force. We have a force on the bottom. We have a force on the top. So I've just very quickly confirmed to myself that I haven't made a mistake, and that term is dimensionless. Now we can move on. We've got pi 1. We can move on to pi 2, the second dimensionless pi term, and now we use the non-repeating variable h in this one. So I've done exactly the same thing. I've written the repeating variables w to the a, v to the b, rho to the c, and now I've written the non-repeating variable in here. We do the same thing. We repeat, we put the dimensions in for each one of the variables, and then we do this matching of exponents. And from this, okay, when you look at the exponents for m, we have m only appears in the rho term, so we have c equals 0. That's correct. When we do it for t only appears in this term, so minus b equals 0. That's correct. So b is going to equal 0. And when we do it for L, we're going to have 1 plus a plus b minus 3c equals 0. So that's correct. And we know that c and b are 0, so b and c are 0, so we get that a equals minus 1. Now we've got our exponents. We can write them back in here. We get h, w to the minus 1, v to the 0, rho to the 0, v to the 0, and rho to the 0 are 1. And so we get that our pi parameter is just the height over w. This is called the aspect ratio of the plate, which of course is obviously dimensionless. Both the top and the bottom have dimensions of length. Moving on now, we can get the third pi term using dynamic viscosity as the non-repeater. So we put the non-repeater in here, and we repeat the same thing. I've substituted in the variables, and it must be dimensionless. So we go through this again for m. Let's just check this. We have 1 plus c equals 0. That's correct. So c equals minus 1. And now for t, we have minus 1 minus b equals 0. That's correct. So therefore b equals minus 1. And here we would have minus 1 plus a plus b minus 3c equals 0. So that's correct. And we know what b and c are. You can check my arithmetic. You get a equals minus 1. You make the substitution now, and we get that the third dimensionless parameter is mu over w v rho. And you might recognize this as the inverse of Reynolds number. Remember, Reynolds number is a characteristic dimension, in this case the width of the plate, times velocity times density divided by dynamic viscosity. And we know Reynolds number is dimensionless, so 1 over Reynolds number is also going to be dimensionless. So we've checked that we haven't made a little arithmetic error. So now in the final step, we put together these 3 pi parameters. We set pi 1 equal to some function of pi 2 and pi 3. Now we don't know this functional form. That's to be determined by experiments. And we have our 3 pi parameters here that we've just determined, pi 1, pi 2, and pi 3. So we get that the dimensionless drag force is a function of the aspect ratio in this 1 over Reynolds number. We recognize that that's 1 over Reynolds number, and any pi parameter can be inverted if necessary. We don't know what the functional relationship is, so we can just invert, for our convenience, we could invert any one of these pi parameters and just change it to some other unknown function. So I've rewritten this inverting here the last term so that we have Reynolds number. So what we get to end rewriting the result, we end up with the dimensionless drag force. This is actually, over here, the dimensionless drag force is actually sometimes called the drag coefficient, is a function of the geometry of the problem, so the aspect ratio of the plates and the Reynolds number. And that's about as far as you can go. It is as far as you can go with dimensional analysis. The unknown function f3 cannot be determined by dimensional analysis. At this point now, you have to resort to experiments, but with greatly reduced effort because you've gone from 6 dimensional parameters down to 3 non-dimensional parameters. I'd like to also emphasize that the pi parameters are not unique. If you picked a different initial choice of repeaters, you'd end up with a different set of pi parameters that would be just as valid, provided the repeaters satisfy those 3 rules that we went over. So just to emphasize, this result stems from the principle of dimensional homogeneity, and it's the same general result as I discussed in the video for part 1. And we've seen a reduction from 6 dimensional variables down to 3 dimensionless variables. And as we discussed in the first video, for fixed geometry, so if you fix the aspect ratio, the dimensionless drag would be only a function of the Reynolds number. And so for a square plate, for example, if you had an aspect ratio of 1, you'd only have to do one set of experiments. You just have to run Reynolds number and measure this dimensionless drag force. And then you'd have to repeat that experiment, say, for a different aspect ratio, say 2. And I've just drawn hypothetical curves here. I don't know what those curves look like. Just to make the point that once you fix the geometry, the dimensionless drag force is only a function of the Reynolds number, and we've demonstrated that through dimensional analysis. And that completes this video.